Carol.
Oh, hi, Charlie.
I have a favor to ask you.
A favor?
Yes, I was wondering, Carol. Could you tell me about why matter is quantized?
Oh, you mean why time is quantized?
Whatever. I really want to know.
You do?
Oh, I'm so excited about it. I just couldn't stop thinking about it all night long. Why, I dreamed about it, Carol. Why is matter quantized?
You mean time
Oh, whatever.
and space?
Oh, is that quantized too?
Yeah.
Well, could you tell me?
Charlie, why are you being so nice to me? You've never wanted to know my theories before.
Well, you're right about that.
Well, what is it you want, Charlie? Do you want a favor? Are you trying to butter me up?
Well,
Come on, Charlie, out with it.
well, I do want a little favor, yes. Just a small one.
What is it, Charlie? Out with it.
Could I borrow your computer?
Why, certainly, Charlie.
Oh, thank you.
As soon as you finish your chores and finish your homework.
Yeah, spoil sport.
I'm not a spoiled sport. I'm just a realist.
You wouldn't think so with all your theories.
Well, now listen. You have to sit down and listen to my theory. Because I have been dying to tell you about it.
I've been dreading this moment.
Okay, now shut your mouth up and listen. The reason that space and time are quantized,
Yes, dear, know-it-all.
is because energy is quantized.
Oh, what? I don't see the distinction.
I mean, what do you mean?
I don't see how one follows to the next.
Oh, well, think about it. Energy is quantized. What is time?
Let's see, a minute?
Time is change.
Oh, I'll buy that.
Yes, time is change, and what's the smallest amount of time you can possibly have?
Let's see, 0 minutes.
No, that's not time at all. That's nothing. But if you have time, what's the smallest amount? I call it delta T minimum. That's the minimum time that you can possibly have.
You say this exists?
Yes, it does. And the reason it is because if you just slow time down so much that the whole universe stops and just one little increment of change occurs, I call that delta T minimum. That's just the smallest change. Like everything else stays the same and one little energy transfer occurs in an atom. Like say a light wave flies into it and then its orbital goes up to the higher orbital because it's got one quanta of energy added to it. That's one change in the universe. And these things are happening all around us.
I've noticed.
Yes, and that we don't notice them actually because there are so many of them and they're all close together and we just see this continuous flow. But when you really think about what time is, it's change. And what's the smallest amount of change you can have? Well, obviously is one quanta of energy being exchanged.
Are you sure that is?
I'm positive, absolutely positive. And so, if you can somehow get that small and slow time down that slow, you will find that there are these little tiny single events that occur in the universe. You can, if you could somehow
become invisible and all that, yes. Oh, yes. You're not into witchcraft, are you, dear?
No, I'm not into witchcraft. I'm into science.
Oh, you do a disservice to science, I'll tell you that.
You say that every time. But anyway, so, now that we know that time is quantized,
well, are you going to tell me space is quantized?
Distance, Charlie, distance is quantized.
And why do you say that?
Well, if time is quantized, and the speed of light is constant, and c equals, well, let's just say that c is distance per time, right? Well, if c is constant, and distance per time, if time is a constant, delta T minimum is a constant value, a very small tiny number, then there must be a corresponding minimum distance that can be traveled in that minimum time by a photon. And we call that delta T minimum and delta X minimum.
Oh, I'm flabbergasted. Can I borrow your computer now?
No, Charlie. Now that we know that time and space are quantized in addition to energy, we can understand how, in the big beginning, light waves were forced to collide with other light waves at that small distances, you know, and they were forced into little circles because they were unstable because they traveled. Their mean free path was bigger than
approached the minimum distance.
Their mean free path was bigger than the distance they were traveling between collisions. So they were forced into little light halos, which we discussed in the last video. You see, this whole thing comes around full circle, and after you watch the last one of my videos, and then you go back and watch the first one, then you understand it. You don't understand it until you've heard the last lecture.
Oh, is this a lecture? Yes, it is a lecture. Oh, there you go on with your lecturing again. Could I go play computer?
Now you need to go do your chores, Charlie, and then your homework.
Oh, shucks. You always ruin everything.